Hi, I'm Casey, and I'm going to talk to you mostly about complex systems. So I'll start off by giving you an example of one. So I used to work at a small startup called Netflix, and they have a microservice architecture. And so here's a diagram of their microservice architecture for their control plane. They've got 7 microservices. And a request that Netflix does streaming video, so from your phone or your website or whatever, it'll make a request to their control plane. That'll come into the microservice C. And because it's a microservice, it doesn't have all of the context that it needs to respond to that request. So C will reach out to A and F, and those are also microservices, so they'll have to reach out. So A will reach out to B and D, and F will also reach out to D and G, and then E reaches out to D as well, and then D reaches out to E, and then E reaches out to A. And so you get this request pattern where you have a lot of things talking to each other, and it kind of looks like spaghetti, and you can't really keep track of it all in your head. I fibbed a bit, though. Netflix doesn't have 7 microservices. It has closer to 100 in the streaming path. So here's a tool that one of my teams built to help visualize that. You can see requests coming in from the internet on the far left. And as those requests come in, the communication fans out among this microservice. And when they've all responded to each other, then the response is collated and returned back to the user. So this is an explicitly complex system because you can see that things are spread apart. But even in a monolith, you probably have different pieces of things talking to each other. If not at the hardware level, then even your stateless stuff talking to your stateful stuff like databases. And ultimately, as an industry, we are moving towards more and more complex systems that look more like this, where a human can't keep track of all of the things talking to each other. Why would we do that? Well, as you're working on whatever project you're working on as an engineer, chances are you're optimizing for some properties implicitly, if not explicitly. Some of the things you might be optimizing for, I find that these are the top 3 that I come across talking to different engineering organizations: performance, availability, or fault tolerance. Nowadays, increasingly, we're optimizing for a 4th one called feature velocity. And that's why Netflix chose a microservice architecture. They wanted to be able to deliver features into production faster. So this is an engineering decision. A lot of companies try to optimize for feature velocity through process, and that can work to an extent, going agile or whatever. There's a lot of practices that you can do there. But this isn't an organizational change. These are things that we try to optimize for through architecture and through engineering decisions. So choosing a microservice architecture was an explicit design decision to optimize for feature velocity. If you have small teams, in the case of Netflix, you can think of them as say about 100 small engineering teams of 5 to 7 engineers each that own small services, the microservices, then they can make changes to those and deploy new features without having anybody coordinate between those. So they don't have to wait for a big push. They can get features out at a more rapid pace. The drawback being that they don't have anybody who's a gatekeeper or who can orchestrate between vastly different places in the microservice architecture. So I want to describe the problem with this with a game. We're kind of evenly divided in, well, we're sort of divided into 3 parts. So we're going to play what's called the beer game. It would take too long to actually divide the class up and play this. So we'll do it Twitch style, where you can watch me play like a simulated version. But if you've been through a master's program, you might have played the beer game. It's like I played a different beer game in college, but this is a specific one that's taught in systems thinking class, where there's 3 players: customers who like to drink beer, retailers who sell it, and manufacturers who make the beer. And usually the way that this is played in a college setting is the class will be divided into 3 different teams, and they're physically separated. and they can only communicate with each other by by passing slips of paper back and forth indicating intent to purchase or goods or money exchanged. And with that setup, we tell a story. So I'll make one up. I'll put some numbers on the screen. You don't have to pay attention, too much attention to these. I'll read through them, but they're kind of just a placeholder. So here you can see the setup of the game, which is in week 0, the first week. The demand for the product, we're mostly engineers, so we'll call it foo beer. The demand for foo beer is 1 case a week, so the retailer sells 1 a week. They keep 2 in stock, the brewer keeps 5 in stock, and so the brewer brews 1 case a week. So what we have here is a system in equilibrium where the demand for 1 case matches the production of 1 case of foo beer. And I'll kind of make up a story to go along with this as we go. So here's our protagonist. We'll call him Zucky the squirrel. Is an engineer like many of us, has a bunch of great ideas, and here he is driving home in his car one day, and he says, you know what, I really just need to build up the courage to like write up my idea and get it out there. And once the world sees how great it is, they'll buy into it, and I'll be rich, or at least famous. So he stops at the convenience store on his way home, and he sees foo beer, and he goes, I'm an engineer, that totally speaks to me. I want 2 cases of that. So the demand that week is for 3. The retailer can only sell 2 because that's how much they had in stock, but they pass their order along to the brewer, who then only has 3 in stock, and so the brewer wants to keep ahead of it, so they manufacture 4 cases instead of the usual 1 that week. So Zucky goes home and writes up his business plan. And his business plan is basically, let's say he wants to utilize the marketplace to solve a problem that we all deal with. So like right now, it's a problem where how do you sell ads to the right people to influence the right politics? And he goes, you know what, I'm going to turn that on its head, and I'm going to set up a marketplace on social media that allows interested parties like, say, Russia, bid on your vote directly. Right? Where we let the market decide who votes for what, and like the intelligence of the market will totally fix this. Awesome idea, and I'll call it the foo beer business plan, the FB business plan for short. And so he publishes this, and it goes to #1 on Hacker News. Like there's all this attention around it. People are like, oh, foo beer, that's great. Like I want to be inspired to write my story out there too. So demand goes up to 35 cases that week. The retailer can only sell 3 because they only had 3, but the brewery wants to stay ahead of this. That's the exponential growth. So they open up a second distillery specifically to manufacture foo beer. Every story that has a protagonist needs an antagonist. Zucky gets a call from the antagonist. I can't think of a name, so we'll just call him project manager. The project manager says, you know what, not only is this a bad idea, it turns out it's illegal. Wah, wah. So word gets out that the business plan's not going to work, and of course Zucky is crushed, but more importantly, like demand for the beer goes flat. The only person who wants to buy it now is Zucky himself because he wants to drown his sorrows. So the demand goes down to 3 cases. The retailer sells those 3, but the brewer now has 250 cases that come in stock, and the next week the demand goes back to the initial steady state demand of 1 case. The retailer sells that 1 case, but all of the rest comes in. So while Zucky has now retired to a beach somewhere and gotten out of tech because of what an unpleasant experience that was for him, we in this game are left with this terrible result. The point of the game is to optimize for customer satisfaction and profit at the retailer and brewer level. And almost always when this game is played, you end up with something like this, where demand was largely unmet, the 35 cases that couldn't be sold because they weren't there. The retailer has 35 cases that they're not going to be able to get rid of. And the brewer has an extra distillery. WTF are they going to do with that? So you almost always end up with this negative result. Why do they play this game in school, other than because professors are mean? It's to demonstrate a principle called the bullwhip effect, where a small perturbation in the input of a system leads to a drastic change in output of the system. And the really interesting thing here is that the 3 teams, they're not stupid. They didn't make any mistakes. In fact, they acted very rationally given the information that they had. And yet the system itself gave this really unfortunate behavior, which is very similar in setup to what we have in complex systems. In the case of the microservice architecture, it's very clear that the teams that build these microservices could be the smartest engineers ever. They could, in fact, be writing code that's provably correct. And yet the interaction between the different parts can result in undesirable behavior. And this is a theme with complex systems. I'll give another example. I don't know if anybody's seen the show Stranger Things on Netflix. 2 people? Okay, cool. That's about right. So it's a show. So I won't ruin it for anybody. But there's in the first season there's a scary part. And so I was watching the first season, and I was on a train, right, which was great ambiance at night, and had like my laptop balanced on my lap and a coffee, and the scary thing happens, and I was kind of surprised, and so I was like, ah. And like my laptop fell to the floor, and so I like cleaned up the coffee and like got my laptop back, and my screen was frozen. So I did what anybody in that situation would do. I hit refresh 100 times, right? And but I was on a train, so like my internet connection was between cell towers. So all of the requests got queued up either on my browser or my OS, I'm not sure which, and then didn't go through until I came back in to service for a cell tower. So what did that look like on the Netflix side? So on the Netflix side, they've got a bunch of different microservices. One has data about customers, users, like me, and another one has information about how the service is personalized for the customers. And they wrote these to best practices, or good, I'll just call it best practices for the sake of this example. So the best practices for something like the consumer microservice are, like, we don't want to, there's too much traffic to put this on one machine, right? So we'll put it on a cluster. And if we've got all of this data, like, we don't need every node in the cluster to have all of the data. We can have, like, some of the nodes have just like a small portion of the data, and we can use like a consistent hash to spread it out evenly among the cluster. And it'll have fallbacks. So if it can't talk to the database to get the data out, maybe it'll have a local cache. So the data will be not quite as fresh, but probably not too much of a big deal. We can serve stuff out of local cache faster if the persistence layer gets overrun. And clusters, because we want to be conscious of our footprint, they have auto-scaling rules. So if we're underutilized, we'll shrink, and if we're overutilized, we'll expand. We'll add nodes to the cluster. And similarly for the personalization service, it will expand and contract depending on the amount of traffic that it gets, and it'll also have fallbacks. So if it can't find a customer, maybe it'll just give some like default user experience. So all of a sudden, 100 requests come in from my one user, which a consistent hash passes off to the customer microservice to just one node, right? Because like the data is evenly distributed. It says, okay, for this user, we'll store all of your information on this machine. So that machine gets 100 requests, 99 of which don't matter. It's only the last one, but it doesn't know that. So, so it's trying to serve all these, which is more RPS than it usually gets. So the stateful layer, the database can't keep up. So instead, it uses that fallback and serves things from cache. Okay, flips over to cache, serves a response much faster. In fact, cache also uses a lot less I/O. So the overall utilization of this cluster goes down. So it's underutilized, so it shrinks. So it picks the most busy node, turns that one off, and moves the responsibility for those customers elsewhere into the cluster. Meanwhile, the personalization service waited for like 95 of these requests and said, you know what, you're taking too long. I'm just going to respond to the user, and I'll give them a default experience. So I'm back in the train, and it finally refreshes, and I see like the default Netflix experience, which doesn't know I was watching Stranger Things. And it has like, I don't know, a bunch of Disney stuff or crap that like I wouldn't normally watch. So I'm like, this isn't what I'm used to. Something's wrong. So I do what any user would do. I hit refresh 100 times. So the same thing repeats, and it overloads one of the nodes in the customer microservice. So it flips to cache, which shrinks the overall utilization of the cluster by a greater percentage this time. So it shrinks, and now it's moving multiple customer data around that cluster. And so the personalization service says, oh, you're really busy. I'll serve more of these default user experiences. So now a bunch of users are getting the default user experience, and they're going, what the heck? That's not what I'm used to. Something's broken. So they click refresh a bunch of times. And now we have a user-induced retry storm. And so all this traffic comes into the personalization service, which hits the customer data service, which flips into cache, which drastically reduces the overall load, which makes that cluster shrink until it's just one server, and then that can't handle the load and it falls over. And that's how I took down Netflix when I was watching Stranger Things on a train once. May or may not be a true story. Probably not a true story. But that's the kind of thing that could happen. Now, what went wrong? Who, as an engineer, made a goof? I don't think anybody did. In fact, those measures to be more resilient are more advanced than the steps that most companies take to be resilient. So it was only in combination, unpredictable combination of those mitigation efforts that something like that could happen. I'll give you another example. I will say service P stands for people, and Q stands for consistency. Here's a scenario where we've got two microservices. A person comes in, and the first time it sees the person, it says, oh, Q, I need you to write this. Here's some user data, write this person. And so it'll write it to a column store, and it'll also write it into cache, in this case, Redis. And then when it wants to read that person's data back out later, it can ask Q, hey, give me this person. Here's the ID. And Q will read it from cache, because that's faster. But like we would put fallbacks in here. So if it can't read it from cache, it'll read it from the column store. And if it can't talk to either, then it has some sort of default response for column store. And likewise, P has a fallback for Q. If it can't talk to Q at all, or if it gets some error from Q, then it will it'll just move along, and it handles that in its exception handling. Then one day, Redis goes down. And so Q, reading these people back, says, oh, Redis is not working. I will pull the data from the column store instead. The problem is, because the cache is much more efficient, over time, utilization of this service queue increased to the point where the column store can't keep up with the amount of traffic, because the cache was handling all of the traffic. So it slows down to the point where it can't respond anymore. So now Q responds up to P, oh, I can't talk to my data stores. Here's a 404. But the fallback that we coded for was an error or not being able to talk to Q. It doesn't make sense from P's point of view that I gave you this person and now you're telling me that the person doesn't exist. That's logically impossible. Who made a mistake here? I don't know that it's reasonable to assume that Q would understand the business logic in P. So really nobody made a mistake here, and yet P has no way of handling that logical error, and so it crashes and takes the whole service down with it. So mostly up to this point, I've been like describing, we're drowning. I'm describing the water. I'm describing like how complex systems can go awry. But I really wanted to convey like this isn't something that you can catch with better testing or looking for bugs. And it's not that somebody's doing something wrong. This is just the normal everyday process of building complex systems. We're going to get weird effects that we don't want. So how do we survive these? So I know what you're thinking. Casey, is the answer simplicity? Can't we just get rid of the complexity? Let's explore that a little bit. There's two kinds of complexity. One is accidental, and to paraphrase what somebody said to me once, accidental complexity is like dirt on the floor in your house. Nobody brings it in on purpose. It's just going about well, I have 2 kids under 4, so sometimes they bring it up, but assuming you don't, like dirt and dust just accumulates through the process of like being alive and having house. Similarly, complexity just accumulates from you doing your jobs as engineers. You're not bringing it in on purpose, and yet there's really no way for you to prevent this from happening. In a couple decades of experience in studying this kind of stuff in software, I have yet to come across a method of sustainably reducing accidental complexity. You can do it in bursts by like taking a complex thing and replacing it with something simpler. I don't know of any practice that like leads to a sustainable way of doing it. At best, I think some practices like TDD and others try to keep the level of simplicity constant, but you can't really improve it. So there's accidental complexity. I don't know of any good strategy to get rid of that. Then there's another kind, which is essential complexity, which is what you put into something on purpose. Why would you put complexity into something on purpose? Imagine I have the simplest database you could conceive of running on my laptop, on my futuristic looking laptop here. So like key value store, doesn't support SQL or anything like that, just key value store running in memory. And I say to you, I need this to be more available, right? That's the kind of thing you would optimize a database for. I want this to be more available. Okay, well, when you close the lid of your laptop, it's not available, so we'll put it on the cloud. That makes everything more available, or so I'm told. Okay, so now it's on the cloud. What else can I do to make it more available? Well, you can put it behind a consistent hash so that there are replica sets, and the request pattern is distributed. It's kind of a well-known best practice for databases. And then once you have that done, then you can switch to an active-active setup where this data is replicating between different clusters. Super available now. In a couple slides, we've also just made it super complex. But we've got a lot of industry experience to say that this makes it more available. Now, what if I asked you, you said, here's my super simple database. Now I want you to make it more available and also simpler. And I'm just going to go ahead and say it, you can't. Like, we got a lot of ways to make it more available that make it more complex. There just isn't a way to make it more available and simpler. So that's essential complexity. In order to optimize for something else that you're trying to build in, a new feature, or feature velocity, or availability, or fault tolerance, or performance, or whatever it is your goal to maintain an application, you have to add this additional complexity. So maybe you're looking at that and thinking, okay, maybe redundancy is the answer. Maybe we can survive these complex systems if we just make them really redundant, like we did with a database. Well, despite designers' best intentions, redundancy can unwittingly increase the chances of an accident by encouraging operators to push safety limits well beyond where they would have had such redundancies not been installed. So in the case of Snook, who's talking here, he was using an example of military helicopters, where they have redundant motors in case, for the rotor, in case one breaks, they've got another one the helicopter can keep flying. So what did the pilots do? Well, they sensed that there was more power there because there's 2 motors running, so they would run them a lot hotter than they're supposed to. That's the same thing that happened in that last example I gave you, where service queue ran hotter on reads than it should have because you had the extra capacity from the cache, which was serving requests a lot faster than the persistence layer could. So redundancy isn't the answer. Redundancy can help with some of your availability, but chances are you're going to be enabling your users to push the limits beyond what they normally would. So redundancy by itself is not going to solve the problem of complexity for us. Maybe it's observability. Maybe if we could just see deeper into the system, we could avoid some of these problems. There isn't a lot that I agree with James' reason about, but this is one of those things. But other things being equal, more complex, the greater the number of bugs, blah, blah, blah. Simpler systems are usually less interactive, but tend to be less evolved with regard to built-in defenses. Thus, fewer bugs can wreak greater havoc in simpler systems than in more advanced ones. But advanced ones are more opaque systems. So you can't observe your way out of complexity because complexity by itself will obscure your visibility into it. Okay, so as a human operator, there's no way that you're going to be able to see enough into a complex system to be able to avoid the bugs that will come with having it. There might be ways that we can control, or at least a framework that we can think about the different kinds of complexity and kind of juggle complexity into ways that we're more comfortable handling them. Economic pillars of complexity comes from economics and describes different things that you may or may not be able to control as you produce or maintain or manufacture something. The 4 pillars are states, the different states of your product or production process, the relationships between those, the environment, and irreversibility. Irreversibility is the degree to which you can do something and then quickly roll it back. So in economics, Ford in the 1920s-ish is the quintessential example of taking advantage of the economic pillars of complexity, because you could have whatever kind of car you wanted as long as it was a black Model T. So their states were greatly reduced. Nobody can really control their environment. Ford also controlled the relationships among their manufacturing process by, instead of having teams that built cars, they had people on assembly lines who could only maybe talk to the person to the left and the person to their right. So there wasn't like cross-company communication, there wasn't cross-functional communication. So the relationships were limited. In software, usually we have a lot of pressure to increase the number of states. That's where features come from. So there's not a lot that we can do there. Best practices or good guidelines now tend to push us in the direction of having more relationships between smaller parts. And certainly see that in like the containerization of the market and then functions as a service and microservices. So that's probably not something you have a lot of control over. Nobody really has control over their environment. But irreversibility is something where software actually has made a lot of inroads. And maybe you can do something to increase your reversibility or reduce your irreversibility complexity. So going from waterfall to agile greatly reduces your irreversibility, because with waterfall, you plan something out, then you spend, however many months building the thing, then you put it in front of a customer and they're like, no, that's not what I meant. It's like, oh, great, it's like impossible to reverse that decision. Agile was built on the premise that like, yeah, okay, plan it out for a week, throw that in front of the customer. No, that's not what I want. Okay, it's easy to roll a week back and then try again. Yeah, that's right, that's right, that's right. Nope, that's wrong. Okay, just roll a week back. We do this explicitly in software architecture now with continuous delivery. How quickly can we roll stuff out and then just have automated ways of rolling these decisions back? Microservices kind of lend to that. And so everything that falls in continuous delivery and a lot of automation helps in the reversibility of software. So in places where you can make inroads there, you are potentially reducing complexity in your overall product management and process, production process. So that might be part of the answer. So building on that, automation. Humans are notoriously bad at monitoring systems that rarely fail. About a month and a half ago, there was a pedestrian killed by an autonomous vehicle. And the problem with automation is, Elon Musk tweeted like 2 weeks ago, like, oh, I underestimated people and I tried to automate too much. Well, it turns out that like Toyota had learned this, 30 or 40 years ago with Lean. Like there's a point at which you can over-automate something as complex as automation, as automotive production, And really, you only want to automate the things for which you have a lot of experience doing manually. So driving seems like something that could be in this realm, but it's not clear how we're interacting with complexity in that case. The driver, or let's say the person in the car, when that accident occurred, a lot of fingers quickly pointed to the person as being the source of error. Oh, the human couldn't navigate the complexity. But that person wasn't doing anything different in the 2 seconds before the accident than they were doing 20 minutes or 25 minutes before the accident. So can you really say that, if they weren't doing anything different, then how were they the cause in that case and not in previous instances? Short answer is automation is not going to buy us wins out of the unpredictable effects of complex systems. What about training? Can we just train people out of doing the wrong things, or teach them enough about the system that they'll know what to do and they won't make mistakes? Generally, this is a general rule, as a response to an incident, put them through training is like a code smell. It's an organizational odor. Starbucks recently had an incident where they had some, let's say they had some racism affected some of their decisions, their management decisions at a shop. So they said, okay, we're gonna shut down a bunch of our shops, and for 8,000 of our employees, we're gonna put them through diversity and inclusion training. And then they'll be trained, and then they won't make that mistake again. The problem isn't that people didn't have exposure to this kind of thing. In fact, it turns out if you expose people to diversity and inclusion training, immediately afterwards, if there's no follow-up and there aren't proper steps taken, you actually increase the likelihood that people will act in a discriminatory fashion. Why is that? It's not because you expose somebody to issues around race or gender or something else and they go, I disagree, I'm going to be bad. No, it's actually they think the opposite. Oh, well, I am now enlightened. I'm aware of my unconscious bias, and so it no longer has power over me. So I can make decisions that won't be affected by these things, and it turns out they do just much worse than they would have had you not given them the training in the first place. So without other things like alignment within the organization and better education processes, training is not going to fix the problem. The actual problem here, and the actual problem with in Starbucks, is organizational alignment among people on what their priorities were. If it were really customer first, it wouldn't matter who the customer was. They would have, the management would have had a different focus. And you can't train your way out of poor company alignment. So training is not going to fix systemic problems or availability issues from your complex system. Compliance. Okay, if it's not the computers and if we can't, through redundancy or automation, brute force our way through the tech or train, maybe we can just force the humans not to make mistakes. Unfortunately, best practices are not derived. They are subjective attributions. What we call best in a complex system is too complex for us to know what the best practices are. So there are no best practices. There are just guidelines that we know from experience, and from experience means we've already gone through a bunch of history with this thing. So you can't take experience and history with a thing and imbue somebody else with it without actually giving them the experience. So likewise, you can't force somebody to be compliant with something that would prevent an accident for an accident that you don't see coming. And these systemic effects, because they're complex, they're beyond what you could imagine. If you could imagine, if you knew that the accident was coming, of course you would have stopped it. And yet we have outages. So at Netflix, they have this application called Chaos Monkey. I managed the Chaos team at Netflix for a little over 3 years. They have this application called Chaos Monkey that selects an instance in a cluster and at pseudo-random during business hours and turns it off. why on earth would they do that? Well, when they moved from the data center to the cloud, they noticed that all of a sudden they were having outages because instances would disappear, because that's a property of being horizontally scalable on the cloud. You will have instances that just disappear. And so instead of just tolerating the outages, they said, okay, well, we want our engineers to solve that problem so that we don't have outages. And at Netflix, there's no organizational structure where somebody can come down and say, all of you engineers, you must do X, Y, Z, these best practices, so that we no longer have outages. That just doesn't exist at Netflix. And practically, it doesn't exist anywhere. But it explicitly doesn't exist at Netflix. So instead, they said, okay, we're going to take the problem that we have, and we're just going to put it right in front of the faces of the engineers, so that they can't get any of their work done until they solve this problem. And so they did, and the engineers did. And they solved the problems for all of these different loosely coupled teams. They all built their services in different ways, different forms of redundancy and fallback and all these other best practices, so that an instance disappearing doesn't bring the service down. And in the past 5.5 years, the service has only been brought down once by a single instance disappearing. Which is a pretty good record for a system as vast as Netflix, with as many servers as they have and as many instances as they have disappearing by accident every day. So Netflix said, okay, that's cool. That's on the small scale. Now let's do it on the big scale. Instead of just turning an instance off, let's turn an entire region off. So we started building what's called Chaos Kong. We're in 3 regions in AWS, Netflix is, and they can't actually turn a region off, something about their other customers being on AWS. So instead they simulate it. But by doing so, they were able to get this process from several hours of like, okay, the East Coast goes down. Now let's move all of our customers to other parts of the globe and make sure that everything is still up and running, down to, now this is automated down to 6 minutes. So close to DNS propagation time, and since people are streaming video and stuff is happening behind the service, behind the curtain, generally this is fast enough that almost nobody will notice. So Netflix thought, okay, this is great. Let's chaos everything so that everything is a lot more stable, and we can survive all sorts of different outages. So I managed the chaos team, which was kind of landed on my plate, and we had Chaos Monkey, and we were finishing up Chaos Kong, and I was like, okay, so how do I do more of this? I don't want to run around and turn things off. So I went around the company and asked, what's chaos engineering? What do you think it means? And generally what I heard back was, oh, that's when we break stuff in production. That, okay, I'm new here, but I'm pretty sure if I break stuff in production, like it's not gonna provide a lot of value and probably not gonna make me many friends. So instead, we sat down to formalize it, and we figured out that what chaos engineering is doing is it's actually allowing us to navigate these 3 things. So I like the tunnel analogy. This is pulled from a framework that Rasmussen developed. But imagine as you're going through your work, you're walking down a tunnel. Hopefully there's a bright light at the end. But you've got a wall on either side and ceiling over you, and the walls are workload, economic, and safety. And those are boundaries. And like in the game of operation, if you touch one, you get zapped and like you're done. You're out of business. So workload, if you work too hard, you get burned out, you're out of business. You get that. And you kind of have a general sense of like, am I working too hard? Similarly for your systems, if they can't handle the traffic that's coming in, you're going to kind of see that. So you're going to have a good sense of how far away the workload wall is. And so you know how far away to walk from it so that you don't touch it. Similarly, economics, you probably kind of know how much you cost the company, and as long as you're not hearing from management all the time that like, oh, we need to cut costs, you have some idea of like how much money you use. And so, and you know that if you spend too much money, then you go out of business. So that's a ceiling. So you kind of have a sense of like whether or not to duck. The problem is, in almost all cases in software right now, you have no signal for safety. Am I about to have an accident? Is the system about to have some unpredicted behavior? No, it's unpredicted, so you don't know. So because you know where those walls are and the ceiling, and you want to stay away from those, over time as you're walking down the tunnel, you tend to drift towards the other one. And so this is referred to as drifting towards failure. What chaos engineering is doing with Chaos Monkey and Chaos Kong is it's providing a signal of here's the boundary. And so now as an engineer with that signal for the safety boundary, you can navigate more in the middle of these three things without hitting them. That's what chaos engineering is providing, that missing safety signal. Formally, we defined it as the facilitation of experiments to uncover systemic weaknesses. And we wrote a manifesto of sorts, the Principles of Chaos, at principlesofchaos.org, to tell you, okay, here's how you would do chaos engineering. Here are our best practices or guidelines for doing it better so that we know when to do it and how to improve ourselves. And then we built a community around this. I started running chaos community days to get the usual suspects in Silicon Valley interested, and then other smaller companies. And so now other companies specifically hire chaos engineers and specifically build chaos engineering teams. And Netflix continued to evolve its practice into what I believe is the most sophisticated example of chaos engineering in existence today. It's called CHAP, the Chaos Automation Platform, that will take these complex systemic interactions between these microservices, create a potential solution space, and then automatically explore, oh, what happens if suddenly this microservice can't talk to this microservice? And it'll run these experiments continuously in production, but with a limited blast radius, so that if something does go wrong, it doesn't affect all the customers. It just affects a small percentage of production traffic. And it runs these constantly during business hours, 8 hours a day, 5 days a week. Just in case something does go awry, we have people who are there. We're not pinging people on call at 3 a.m., as usually happens with outages. So how do we survive the weird effects of complex systems? I didn't give you a full answer, but I think chaos engineering is definitely one of the better tools that we have to supply that signal for the safety boundary. I like the analogy of a well-run kitchen. Hopefully you've had the experience where you've been in a kitchen and like a lot's going on. Hopefully you've had the experience where you've been part of that, where a lot of people are making stuff and you're making stuff, and it all just kind of works, and nobody's really saying like, you move over there so that I can move through here. You just kind of like find your way. And then maybe you've had the experience where you're in that kind of situation, and then you finish like whatever you're making, you know, the garlic toast or whatever, and then you stop and you look around, and all of a sudden that's when you find that you're in the way. And one way to understand what's happening there is everybody kind of subconsciously has a mental model of what, or an understanding of what you're doing when they kind of understand what you're trying to achieve. And so everything just works without explicit coordination. But the minute you stop, they no longer know what you're doing. So they can't accommodate for what you, in this case, aren't doing. So now all of a sudden you're an obstacle. And you find like, oh my God, before everything was just moving, and now I just need to get out. That's a great example of a complex system. It'd be really hard to write the code to like run all these people doing this. That just works when people have practice being in the work and have signals for when they're about to screw it up. So embrace the complexity and navigate it. Don't try to reduce it. You can't really remove it. And trying to control it through process is just going to backfire. Provide opportunities for teams to practice working together. So this chaos engineering, a lot of practitioners run frequent game days. If the fire alarm went off, everybody would generally know what to do in the case of a fire alarm because we've been practicing that since school. Similarly, when your system goes down, that's not when you want everybody to figure out like how to work in that kitchen together. Give them a little bit of practice and it'll go a lot better. Tolerate inefficiencies. Being software engineers, a lot of us have been trained to make things as efficient as possible. It turns out efficiency is very brittle. So you have to, particularly if you're in management, you have to find a way to tolerate inefficiencies that are still highly aligned towards the common goal. That makes a much more robust, complex system. And communicate the safety margin. And there's no silver bullet for communication. There's no tool that's going to do it for you. This is talking to people, alerts, emails, documents. However, like every organization, I'm sure you're struggling with growing as quickly as you are, and how do you communicate the right things to the right people? There's no silver bullet for that. You just have to do it as many pathways as you can. Include the safety margin in there. Hey, I think we're running a little too hot over here. Hey, this feels unstable. That signal needs to be part of your manufacturing maintenance operations process. So at the end of the day, humans create the resilience. Your tools don't. So there's kind of the answer to that question. How do you survive the unwanted effects of complex systems? The answer is kind of in this slide, but I'm not explicitly giving you something on a silver platter. I wrote a book on this. I don't think there are many copies here, but it's free online, Chaos Engineering. I work at a company called Backplane.io, which takes a lot of the problems that Netflix faced in the traffic space, and now offers that as a service type thing. If anybody wants to talk to me about that, cool. I'll be around, and I'm very easy to find online if you have any other questions. Thanks.